record. Then share my screen. Okay, can you guys see my pen and paper?
Yes.
Cool. Awesome. Okay, so last time we left off with using prime factorization to reduce fractions. We looked at how we can convert improper fractions to mixed numbers and vice versa. And really, that gives us a lot of skills to be able to work with fractions. We understand that a fraction is a representation of a part of some whole object. We were talking about pizza parties last time, and we talked a little bit about if we divided that pizza up into 8 slices, then each of those slices would be worth 1/8 of the whole pizza. So that works with really anything. You could think about bars of chocolate that are split up into maybe 9 little cubes or 9 little squares. Then each of those pieces of chocolate would be worth 1/9 of a chocolate. And so we have to think about those fractions as being a different kind of currency or different denomination. And we have to think about having a different exchange rate. So if we were, let's say we're back at a pizza party and we said, okay, I have a pepperoni pizza, and excuse my spelling because there we go, I think that's right. We have a pepperoni pizza. And let's say that we cut this into our traditional 8 slices. And it's just a hot and ready from Little Caesars, you know, nothing fancy here. We didn't have money for Papa John's this week. That's okay. We still had enough for Crazy Bread. Then we maybe have a veggie pizza over here. But our friend ordered a veggie pizza and they wanted special conditions for their pizza. They wanted to just cut into 4 slices because they sort of like bigger slices. So we understand that each of these slices here for our pepperoni pizza is worth 1/8 of the whole pizza. And 1/4 of the pizza is what we could call one of these slices over here. Okay. For fractions like this, where the denominators are sort of related in that, you know, one of these denominators is a multiple of the other. So 8 is a multiple of 4. What we could do is just cut this veggie pizza into extra slices in case we wanted to trade or exchange or, you know, shift some pizzas around, some slices. So let's say that this veggie pizza, we went ahead and, you know, while our friend was away, we cut it into a normal pizza like normal human beings and had 8 slices. So now each of these pieces is no longer worth 1/4, they're worth 1/8. So now we can make a 1-to-1 trade. So if I had, let's say, 3 of these slices that I was going to eat, and then I took 2 of these veggie pizzas because, you know, maybe I've run a lot of miles, I've earned the carbs that I'm about to ingest. How would I add, you know, 3/8 plus 2/8? What should I get here when I add this? Does anybody know?
5/8.
5/8.
You're just adding it straight across and keeping the denominator the same. Is that correct? The
Yeah,
denominator?
that's exactly right.
Okay.
Is anybody confused as to why we should keep the denominator the same? Or can anybody explain why we would keep the denominator the same?
Because you took the veggie pizza and you altered the way it was cut to match the same as the pepperoni. So it
Right.
became 8ths. Now, since it's 8ths, both on pepperoni and both on veggie, that denominator must remain the same because there's no differences between that.
Right, that's a good explanation. Another way of putting it is that they're the same slice size, right? They have the same denomination. We're working with the same currency. So the exchange rate is the same. another way of thinking about this, and I like to talk about math as though it's learning a foreign language. We can think of this as a linguistic approach. For this pizza, we had 1/8. I'm sorry, we had 3/8 of that pizza, right? And we're adding that to 2 of these objects that we're calling eighths. So if we have 3/8 plus 2/8, in the same way that if you had 3 apples and you added 2 apples, you should have 5 apples, right? So that's a way you could think about it linguistically. It just sort of is common sense here that we should have 5 of these things that we're calling eighths. But then, you know, if you needed to convert that back into math, we could have 5 what we're calling 1/8. And if we have 5 of these, we'll see when we do multiplication with fractions that we should have 5/8, that this is going to be the same thing. But yeah, you're absolutely right. We're just adding the numerators, but the denominator stays the same. Now that's only if you have a common denominator. So you have the same size of slices. So when you add, well, I'll just put this note here so we can make it very clear. When you add or subtract fractions, with the same denominator, you're going to add or subtract the numerator, and the denominator stays the same. I'll give you guys a moment to write that down if you're writing. Remember, the video is going to be uploaded later, and I'm also going to put these scratch notes up later. Okay, so let's do some examples. Let's say that I had a pizza and it was cut into 16 slices, and I took 9 of those pieces, so 9/16, and I wanted to add that to 5/16. What should I get if I add these 2 fractions together?
14/16.
Yeah, 14/16. Again, we're just adding the numerators and keeping the denominator, the slice of pizza, the same. Both of these pizzas, if you can visualize them, both of the pizzas were cut in the same way. They have the same size slice. But the number of slices that we're combining, that's what we're really adding. That's what we're really talking about. So we have 14/16. That's going to be our fraction. Now, this fraction, if you take a look at it, some of you might realize that it's not fully simplified. Okay, so for most of the problems that we work well, for all of the problems that we work in this class, we're going to have to simplify or reduce the fraction once we get our result of that addition or subtraction. So we'll use our prime factorization to reduce this. So if you remember, we'll prime factorize (14) and 16. And remember, we're going to use this tree method to break down each of these composite numbers into their prime factors. So we can break down 14 into 2 times 7. And those are prime, so we can say that that tree is complete. We've fully broken down 14. For 16, we can have 2 times 8, 2 times 4, and then 2 times 2. We're now, all of our prime factors are 2, 2, 2, and 2. So we can now rewrite this fraction as 2 times 7 on top. And then our prime factors here are 2, 2, 2, and 2. So I'll just write 2 times 2 times 2 times 2. Once you have that, we're going to cancel out our common factors by division. So if I have a 2 on top, I can cancel out the 2 on the bottom. So that means that I have 17 remaining on top. And I just have 2 times 2 times 2 on the bottom. Nothing else here cancels. So I'm just going to go ahead and.
I'm sorry, Professor. Is that supposed to be 17 or 7?
Why did I put 17? It's supposed to be 7. My bad. I think I might have looked at the 16 and the 7 and I threw a 1 in there for no reason.
Okay, thank you, sir.
Yeah, no, good catch. Thank you for that.
You're welcome, sir.
So we had broken down 14 into 2 times 7, not 2 times 17, right? In any case, despite my mistake, these common factors of 2 will cancel out and we have a 7 left over on the top, not a 17. And then we have 2 times 2 times 2 on the bottom. So 2 times 2 times 2 is 4 times 2, which is 8. So we should have 7/8. So that's going to be our final answer, 7/8. That is the fully simplified number of slices or amount of slices of this pizza that we had. So in that sense, 14/16 is an equivalent fraction to 7/8. And the alternative way that you might have reduced that fraction is you might have just divided a 2 out of both of those, and you would have gotten 7/8. So if you can see it, that's great. You can go ahead and divide out your common factor. But the prime factorization tree, again, is a skill that you're going to need later on in the semester. And it's really easy for you to see all of the prime factors lined up, cancel out the ones that can cancel, and then what you have at the end is fully reduced. A lot of times, if you have really large numbers here, you might divide out a common factor that seems obvious to you, but then you might think that it's fully reduced at that point, and you might be leaving a prime factor trapped in there that you could have canceled out. Okay, so I think that the prime factorization is more thorough. So that's what I recommend. Okay. I'm going to give you guys some practice problems and then throw you guys into some breakout rooms to see if we can add and subtract. And I know we just did an addition problem. Subtraction should be the same process. So let's do.
Professor, can you recap on how to determine if a number is prime or not?
If a number is prime, then it can only be broken down or written as the product of 1 and itself. So the common primes are going to be 2, 3, 5, 7, 11, 13, and so forth, right? If it has more than one common factor pair, then it is a composite number. Does that make sense?
Okay.
So its only factors are 1 and itself. So if I asked you, 23, can you break that down into a number times another number?
Is it because it's an odd number that we couldn't? Or
Most primes are odd, but that's not the end all be all because 2 is also a prime.
Gotcha.
Yeah. I think that 2 might be the only prime number because everything else can be divided up into 2 times something else. Like 24 is not prime because you can write it as 1 times 24 or 2 times 12 or 3 times 6. No, 3 times 8, 6 times 4. See, and I had multiple pairs of factors that multiply to make 24. So that's how I know it's composite, as opposed to 3, which can only be broken down into 3 times 1. So 3 is prime.
Gotcha.
So it's basically if the number multiplies into something. That's what you're saying, right?
If
Like you said, 23.
like 23 can't be broken down into anything other than 1 times 23.
Right.
Yeah,
Okay.
that it's not divisible by anything but itself and 1.
Okay. Okay.
Yeah.
Got it.
5 ninths plus 1 ninth. Let's do 4 sevenths plus 9/7, 3 9/7 minus 13/7, 4 10/3 plus 14/3. Okay. So take a moment to write these down. I'm going to open up some breakout rooms, and then actually I'm going to throw one more in there because I feel like we don't have enough fractions subtraction. Now we'll get to some subtraction later. I'll throw some more examples of subtraction in the next little bit. So write these down. I'm going to open up some breakout rooms and then just go ahead and accept the invitation to the breakout rooms. I'm going to make 3 of them. You guys are randomly assigned, so there's 7 participants per room. So just work these out, and if you have any trouble, just ask each other, for some help. And I'm going to be jumping into the breakout rooms to see, what questions we have. And the rooms are now open. Okay. I think everybody is returning to the main session now. And it sounded like everybody, had a pretty good conversation about these. You guys were able to get them done pretty straightforward. So let me run through these. The first one, again, we're just going to add the numerators, keep the denominator the same because it's the same slice of pizza, same slice size. This is 6/9. What you could do then is prime factorize, or just if you see that both of these have a factor of 3, you could divide out a factor of 3. But I like to just prime factorize. So this is 3 times 3 here on the bottom. We can cancel out a common factor of 3. So we should have that equivalent fraction of 2/3, and that should be our final answer, fully simplified. I'm just going to roll through these because I think that we got them. This one we're adding again, so this should be borrow 1, you get 10, so this should be 13/7. That's an improper fraction. You can leave it as an improper fraction because this one is fully simplified. What we would say is that 13 and 7 are mutually prime. That is, they have no common factors. So there's nothing to do here. We can leave it at that. But if you wanted to sort of flex your skills of converting this into a mixed number, what you would ask yourself is how many times does 7 go into 13? It goes in one whole time. You would take away the 7, right? Because we're doing long division. And then what would be the remainder? Well, the remainder should be 6. So 6/7. Either of these would be fine. I would say I prefer the fully reduced improper fraction, though. That's what I would go with. But these are both acceptable. And we could double check that this is the correct mixed number form, because 7 times 1 would be 7. We add that to 6. That should get us our 13. So we would have 13/7. So these are both equivalent fractions. Over here, you got to be very careful to do the problem as it's stated and not to flip this subtraction in your head. 9 minus 13 is -4/7. Again, the 4 and the 7 are mutually prime, so this thing doesn't reduce. So we're done there. We're not going to worry about the mixed number here. Because it's not an improper fraction. That's why we don't have to worry about mixed number. And then this one, finally, you could add them straight up and you should have gotten 24/3. And this fraction can be fully. What's up? We have a question? Okay. So now you could simplify this further if we wanted to do some prime factorization. 24 is 2 times 12. I know you guys can't see that. This is 2 times 6 and 2 times 3. So I could write this as 2 times 2 times 2 times 3 if I wanted to, over 3. The 3's will cancel out because that's a common factor. And then all I have left is 2 times 2 times 2, which is 8. And so we have a whole number. 24 divided by 3 is 8, so that makes sense. Does anybody have any questions about these?
No.
Cool. Yeah, I think that you guys were able to do those and just breeze through them, so that's really nice. Now, the difficult thing that students have a lot of problems with is adding and subtracting fractions that don't have a common denominator. Okay, so we need to get this down pat because that's going to be a super important skill. So adding and subtracting. Fractions with different denominators. So we're going to take it back to the pizza party. This time we have one pizza that, again, like a normal human being, we cut our pizza into 8 slices. But then maybe we have a friend that cuts them into fourths, like I said before. And let's say that I ate, or maybe I took maybe a little bit more than half of my pizza, and that's how much I ate. So I ate this highlighted green part. And then my friend took half of their pizza. How much did we eat among us? How much did we eat in total? Well, how would I write this out? Can anybody venture a guess? What plus what?
It'd be 5/8 plus like a half or 1/4 or 2/4.
2/4.
Yeah, if we're gonna stick to the denomination of slices as we see them,
Okay, yeah,
we could
2/4.
write that as 2/4. But it's excellent that you can write it as 1/2. So this is the exact same thing as writing 5/8 plus 1/2. That's what we mean when we say half. But let's stick with this for a second. Notice that when we had the same denomination of pizza, we could just add the numerators straight up and we could keep the denominator the same. Does anybody know how we would do that now that we have different denominators?
We have to, I guess, I'm gonna wager to say that the number 4 denominator has to be multiplied by 2 to get to 8, but then we have to do the same thing to the 5/8. So we have to find a denominator that's the same. So whatever we do to the right side, we have to do to the left side. Am I
Not
hearing a
necessarily.
barking?
Yeah, I also hear the barking.
Yeah.
I'm not sure if somebody has a dog or something, but you can go ahead and mute yourself if you have some sort of animal. I'm pretty sure my rabbit is not barking. She tends not to do that because she's a rabbit.
My cat don't bark.
So aren't you supposed to find the least common denominator?
Yeah, that's what we say, right? We find the least common denominator. And Michael, you're absolutely right. We need to somehow process these so that we have the same denominator. And we could do that by multiplying this denominator by 2. But really, I want to be very careful about the way we talk about this. We're not really dividing this, or I'm sorry, we're not really multiplying this by 2. What we're really doing is saying, well, if I look at this pizza over here, I can cut up each of these 4 slices, right? These 4 components. If I divide them in half, I will have the same number of slices and the same size of slices as I do for this first pizza, right? So right now I'm looking at 2/4, but if I went ahead and said, let's go ahead and cut them up so that they're equal size, and let's just do that to the whole pizza, like so. Well, now I have 1, 2, 3, 4, 5, 6, 7, 8, right? We have a denomination of 8 for each of these slices. So now how many eighths of a pizza does this 2/4 represent?
4/8.
4/8.
4/8. So I can rewrite this as 5/8 plus 4/8. And that way, we didn't have to do anything to this other pizza because we just needed to process one of it in this case, with one of the pizzas in this case. So we have the same slice. But it's almost as though we divided that pizza up such that each of these slices got cut in half, right? We cut them into 2 smaller slices. So you can think about taking this fraction and multiplying both the top and the bottom by 2. Now, you're really not multiplying the top and the bottom by 2. What you're doing is you're multiplying this fraction by 2/2. Can anybody tell me what 2/2 reduces to?
1.
Yeah, that would be 1. So when you multiply 1 times anything, does it change the value? Like, what is 1 times 3?
3.
And what is 1 times 25?
25.
And what is 1 times 2/4?
It's 2/4, right?
It's 2/4. It doesn't change, right? Multiplying by 1 does not change the value. So if we multiply this by some convenient form of 1, like 2/2, well, that in effect changes our denominator to 8, what we wanted, and it changes the numerator to, but it doesn't change the value because really this is just 1. We've only changed what this fraction looks like. And that's a little bit trippy. So if it doesn't click automatically, I'll sort of show it in a few more examples. But now that we have a common denominator, we're going to add them the same way we would in the past practice problem. So we're going to get 9/8 here, and that's a fully reduced fraction. So we're good there.
So would you say that it would technically benefit us if we come across a similar situation like this to always draw out a pie graph and
No.
kind of complete it in the form we just did?
It'll help for fractions like when you're practicing. It'll help for fractions that have small denominators.
Right. But
But
when you're dealing with larger items, then
yeah, you're going to be drawing, like if you have 17/52, you don't want to take a circle and then cut it into 52 even slices.
right.
And then add or subtract that. Like you're just going to waste a lot more time. So I'm going to
So-
try to give you some tips on how you would do this without having to draw a diagram. But this is the reason why we need common denominators, because we need to be able to trade pizzas, exchange with the same currency, with the same denomination, the same size of slice. So now let's take a look at some problems. Let's see. Let's do 1/7 plus 1/9. Okay, so I'm not going to ask you to draw out a pizza every time or a couple of pizzas every time you do this, because it's just going to become really frustrating and tedious. So what we need to do is come up with some method of changing these fractions so that we have a common denominator. Now, a lot of times what you can do is a process called finding the least common multiple or the least common denominator. But I'm going to call it the least common multiple right now, because what we'll do is list out the multiples of 7 and 9, 7, 9. And if we counted by sevens, we could get 7 times 1 is 7, 7 times 2 is 14, 21, 28. What comes next? 35, 42, 49. What comes after that? It's 56. And then 63. Okay, that was a lot of thinking, right? I had to go through the times tables in my head. We'll have to do the same with 9, 9, 18, 27, 36. What comes next? 45, 54, and then 63. So notice that I stopped here at a convenient location where now the list of the multiples of 7 and the list of the multiples of 9 have something in common. We have this common multiple, and it's the first multiple or the smallest multiple that has shown up where they are the same. That's why we call it the least common multiple. And that's what tells us that our least common denominator for these fractions is going to be 63. So I need to rewrite these fractions having 63 as our denominator and add them. But somehow I need to process these fractions so that their denominators change, but that will naturally change their numerators. And so what you need to do then is for the first fraction, 7, I needed to multiply that by 9, 1, 2, 3, 4, 5, 6, 7, 8, 9, in order to make that turn into a 63. So what I really need to do is multiply this by 9 over 9. So 9 times 7 is going to give me that 63. And I need to multiply 9 times 1 on top. So 9 times 1 is really convenient. That's just going to be 9. And then I need to do that same thing over here, except this time 9 times something will give me 63. And it should be 1, 2, 3, 4, 5, 6, 7. So this should be 7 over 7, changing this fraction into 7 over 63. Now that I have a common denominator, I can go ahead and add 9 and 7, and I should get 16 over 63. And that does not reduce. I'm fairly certain. Starting to doubt myself. No, yeah, it doesn't reduce. So if I think about what are the factors of 16, to see it, does this simplify? You could think about it as 16 is 4 times 4, which you could break those down into 2 times 2 times 2 times 2. So that's the prime factor.
I have a quick question.
Yeah.
Did you flip the numerators to get 9 and 7?
What is that?
How did you get the 9 and the 7? 9 over 63 and 7 over 63?
We
How'd you
found
get
that,
the numerator again?
well, whatever you multiplied the denominator by to get this 63, that common denominator, you have to
Right.
multiply that same number on the top.
Yeah.
So 9 times 1 is 9.
Okay,
And
so
then-
it's by, oh, okay.
And then for this one, we had to multiply the 9 by a 7 in order to change it to 63. So that means we had to multiply a 7 on the top over here. So
Okay.
7 times 1 gives us this 7.
Okay.
Yeah.
Sounds good.
So once we added those up, we get 16 over 63. And then we're just verifying to make sure that there's no common factors, so we can't simplify this any further. So 16 breaks down into 2 times 2 times 2 times 2. If you do your prime factorization tree, you'll find that that is true. 63 breaks down into, well, we did 7 times 9 to get it. And then the 7 doesn't break down, but the 9 does. So this would be 7 times 3 times 3. And we have no common factors. So that means this answer must be fully simplified. So reducing the fractions adds a little bit of complication to our lives. But let's see about doing some more of these examples. So we need to do 1/4. Let's do minus 5/8. And you guys can, write them down and then work them out along with me. See if you can beat me to it as I sort of write these out. I'm going to do all of these as subtraction problems. So 2/15 minus 1/5. We'll do 3/4 minus 3/5. Okay, so does anybody have any idea how we would go ahead and process this first problem?
We're gonna find the LCM
Mhm.
for the denominators. In this case, we're gonna go 4, 8. So right there, that's 2. So
Yeah.
on the 1/4, we're gonna multiply that 4 by 2, and we're gonna get 8 for the denominator. And then for the numerator, we're gonna multiply 1 times 2, and we're gonna
Yeah.
get 2.
Absolutely.
Then on the second number, the 5/8, that's already at its LCM 8. So
Yeah.
that's times 1.
So we can leave it alone, or you can multiply times 1 if you want to, practice
Just-
that process. I would just leave it alone, but I'm just going to write 1/1 here just to show
Yep.
that nothing is changing.
And then we'll just go ahead and bring that over to our new equation, 5/8.
Yeah. So
So
we
now
have
we have
2
2 minus 5. Is that going to be -3?
Yeah, absolutely. So we have -3/8. That fraction does not simplify, and we're done. Good stuff. Anybody want to take a run at number 3? Or can anybody tell me what the LCM or the LCD, least common denominator, for this fraction or set of fractions will be? Because sometimes once you start to, get a feel for it, you can sort of look at it and guess.
For number 3, it would be like 3/3.
Multiplying what by 3/3? Which fraction?
The 1/5.
Yeah, exactly. So we're going to take the 1/5 and multiply that by 3/3.
I don't want to say multiply by 3 because I don't know. Sorry.
Yeah, no. So you can say we are multiplying this by 3/3 because in some sense, 3/3 is just 1. And so if we multiply anything by 1, nothing changes. So it's okay to say, it's okay to say that.
Okay. So
Wait,
it'd
how did you
be-
get 3/3 though?
Well, the LCM has to be 15, right? Because 15 is the common multiple of 15 and 5. Right? Like you're not going to want to write, the multiples of 15. So 15, 30, 45, and so on, right? You could do that. And then we could do 5, 10, 15, 20, 25, 30, 35, 40, and so on. But among these lists, what is the smallest number that both lists have in common? Well, both of these lists have a 15. They both have a 30. At some point, they will both have a 60. But actually, they'll both have a 45 here. But it's called the least common denominator, least common multiple, because we want the smallest common multiple. In this case, it's 15. So I think Kaylee is the one that was running through this problem for us. She identified that all we need to do is change this 5 into a 15. So we just took 3/3 and multiplied it by this fraction. And you'll see that we'll now get, our new problem is 2/15 minus 3/15.
Yeah.
And then we finish this up, right?
Yes, and then when you subtract that, you'd get 9/15.
Ooh, be careful. How'd you get 9?
Wait. Oh, I put 12. I'm so sorry.
No, you're good. Don't worry about it. We're just doing 2 minus 3, right?
Yeah, so it'd be
I got
-1
1 over here.
Should be -1/15.
There you go.
Again, don't flip it in your head and say it's +1 because it's not 3 minus 2. It's 2 minus 3. If you had $2 and then you spent 3 of those dollars, you owe the bank $1. So -1, -1. Cool. And then just to finish this off, if you look at these fractions, as opposed to listing out the multiples, one thing that you could do to just go ahead and find that LCM really quickly is just multiply this fraction by this denominator, right? So I would multiply this fraction by 5/5. And I would take this fraction's denominator 4, and I would multiply 4 over 4 on the other side. And that will allow us to change our fractions to have denominators of 20. And then we just need to figure out what the numerators change to. So 5 times 3 in this case is 15. 3 times 4 in this case is 12. And then 15 minus 12 should be 3 over 20. And that fraction does not simplify, so we're done. It's fully simplified.
The way you just did that by swapping those denominators over, could we use that tactic on all of our LCMs?
Yes, you could. But you always want to make sure that your final answer is fully simplified. Because for some of these, like for this one, let's say, we only processed one of the fractions by multiplying it by 3 over 3. We didn't do anything to this other side. So if you had crossed it and did 15 over 15 over here, and then you did 5 over 5 over here, you would get the exact same answer, but the numbers would get really big and you would have to simplify at the end. Okay. So if you want a consistent process, you can just swap those numbers like I did on this problem. Just be sure that you fully simplify your result because it won't be simplified most of the time.
I got you. So it's safe to say that locating the LCM would probably be the ideal way just to make sure that you're getting the lowest
Yeah.
possible answer.
Yeah, to where it's like fully reduced and you don't have to do any extra steps.
Okay.
But there's
Thank you,
there's so many ways to process these that you know, when I'm working some problems, I'll use one method because it'll jump out at me that this is the simpler thing to do. When I'm working another problem, I'll use a different method because in that case, some other method is going to work a little bit better. And that being able to discern when to use which method just takes a whole lot of practice. So practice what you feel comfortable with, what consistently works for you, and then just build up speed from there.
Thank you.
Okay, so we talked about addition and subtraction, and we don't have a whole lot of time to talk about multiplication and division of fractions, but it turns out that multiplying and dividing fractions, even though we probably think in our heads that like multiplying and dividing whole numbers is a harder process than adding and subtracting whole numbers, it turns out in the world of fractions, multiplication and division are super simple. So let me give you the rules for multiplication. Well, there's only one rule for the multiplication. Multiplication of fractions, you're just gonna multiply the numerators, multiply the denominators, and then simplify the fraction, simplify the result. I'll say simplify the product because that's how we want to talk about multiplication. The result of multiplication is the product. So that's our 3 steps for multiplying fractions. I will say this note, for multiplying and dividing fractions, we don't care about common denominators at all. Least common denominator, you're only concerned about that for addition and subtraction, not multiplication and division. So if I give you an example here, like 5/3 times, let's do 4/7. I'm just going to multiply straight across. 5 times 4 is what?
20.
20. Yeah, there we go. And then 3 times 7 is what?
21.
21. And then we're done. It looks like to me, if you needed to inspect this to see if it reduces, 20 reduces to 4 times 5. And then you could break that up into, 5 times 2 times 2 if you wanted to. This only breaks down into 3 times 7, where both of those are prime, but we have no common factors. So since we have no common factors, that means we're done. We have successfully multiplied these 2 fractions together. Just multiplying straight across. Let's look at another example. Okay. 5/7 times 11 over 15. Can anybody tell me what 5 times 11 is?
55.
55.
And does anybody off the top of their head know what 7 times 15 is?
105.
It's 105? I'm gonna take your word for that. Actually, I'm not because I'm verifying over here in my calculator. Yeah, we're
Yeah,
good.
it's 105.
Okay. Can this fraction be simplified?
Yes.
Yeah, and do you want to use prime factorization or do you want to just divide out the 5s?
5.
Divide out the
Divide out
5s.
5.
Yeah, let's just do that. Okay, so I'm just going to divide out the 5s. And we should take the top back to 11. And then 105 divided by 5 should be, I think it'll be 21. And that's fully simplified. But I want you to note something here. And that is when we multiplied 5 times 11 and 7 times 15 in the original fractions, notice that I just put a big fraction bar and sort of connected them together. We could break down this into 3 times 5, this 15, and rewrite this as 5 times 11, 7 times 3 times 5, right? Because 3 times 5 is our original 15. But once we do that, we can cancel out the 5s. And then all we're left with is our 11 and then 7 times 3 on the bottom, which is the 21. Well, it turns out you can multiply them out and then figure out how to reduce this later. Or if you identify that there is some common factor already in this multiplication, you can cancel out that common factor at the very beginning. It's a neat trick. Okay, let's look at another example. Let's do 2 1/3 times 27 over 29. Well, this is sort of a pain in the butt because we have a mixed number here. We need to convert that to an improper fraction before we can actually get started. We want to start with everything being fractions, not mixed numbers, okay? So can anybody tell me what this is going to be once we convert it to an improper fraction?
Are you
7 over 3.
multiplying 3 times 2 plus 1?
Yeah, that's exactly the process.
Okay.
So I think somebody else said it.
7 over.
Yeah, it's 7/3. So 3 times 2 is 6, plus 1 is 7, so we should have 7/3 here. And then we're going to have that multiplied by 27 over 29. Does anybody know if 29 is prime, if it's divisible by anything? One way that you might check is just take 29 and start dividing it by numbers that you think it might be divisible by. So I might divide it by 3, and I'm not getting a whole number, so that doesn't work. 29 divided by, don't know if 7 will work. 29, well, really, we want to start with like 2, 3, 4, 5, and so on. 29 divided by 3, we did that. 29 divided by 4 doesn't work. 29 divided by 5 doesn't work. I'm pretty sure that 29 divided by 6 won't work because 3 didn't work. 29 divided by 7, we already tried that. 8 doesn't work. And I'm pretty sure 29 is prime if we were to go through that whole process. So to me, it doesn't look like this has any common factors. We're just going to multiply straight across and then, that'll be the deal. So we can use our calculator to multiply these numbers since 7 times 27 is sort of a large number. 7 times 27 is 189. 3 times 29 is 87. And the whole reason for me trying to see if they had common factors here or if they were prime was to see if I could simplify or reduce something beforehand. Actually, the 3 and the 27 had a common factor. So you might say, well, it's kind of hard to tell what common factor they're going to have here. But remember, I'm sort of examining what's on top and what's on the bottom to see what is divisible by something else down here. So 27 is divisible by 3. So that means that I should be able to divide out a 3 from both of these. Let's check that out. So I might go into my calculator and say 189 divided by 3 is 63. 87 divided by 3 is 29. So this should be 63 over 29. And we said 29 is prime, so that has to be no common factors here. Oh, unless 29 goes into 3, unless it goes into 63. So 63 divided by 29, don't think that works, and we're good. Okay. Well, I know that I breezed through that. It's going to take some practice. If you get stuck on the homework for the multiplication stuff, come to my office hours, come to Math World, because the last thing that I need to share with you guys is how do we divide fractions? And I'm going to give you this really simple heuristic for dividing fractions. Heuristic is just a fancy way of saying a rule of thumb. What you're going to do is keep, switch, flip, and you'll see in a second what I mean by this. So for our first example, let's go with 1/3 divided by 1/2. Okay. So what do I mean by this keep, switch, flip? Well, we're going to have to change our problem to multiplication because it turns out that dividing fractions is really difficult. So instead, what I want you to do is keep in mind that when we're dividing fractions, remember this keep, switch, flip. Just repeat that phrase in your head. We're going to keep the first fraction. We're going to keep it the same. We're going to switch to multiplication. And then we're going to flip this fraction to what we call its reciprocal. So we're going to flip the fraction so that the denominator becomes the numerator and the numerator becomes the denominator. So what do I mean by that? We're going to rewrite this as 1/3 times 2/1. So now that we've done that keep, switch, flip, we're back in the world of multiplication. And the rule for multiplication is just multiply straight across. So now we have 1 times 2 and 3 times 1. So our fraction should be 2/3. And that's our answer. Okay.
And it doesn't matter how big or small the fractions are in this
Nope.
instance for dividing, the process remains the same for keep, switch, flip.
Absolutely. You're dividing
Okay.
fractions regardless of what those numbers look like, regardless of how big they are, regardless of whether they are positive or negative. You're going to keep, switch, flip, and then just multiply straight across.
Now, does this still require the simplification method as well?
Yes, you always have to simplify the result of your fraction operation. Yeah, regardless of the operation we're doing, whether it's addition, subtraction, multiplication, or division, you take that result, whatever you get when you're done with that operation, and you have to see, is this fraction fully simplified?
Gotcha. Thank you.
Yeah. So let's do 4/5 divided by 8. Can anybody tell me what we need to do here?
You're gonna change the 8, which is 8/1 to 1/8.
Yeah, exactly. So if you're not aware, you can write any whole number as the whole number over 1.
Yeah.
It doesn't change the value. It's like saying if I have 8, 8 is the same as 8 divided by 1. So we can write this as 8 over 1 because a fraction is just a division problem. Hasn't changed the value at all. Then we can go ahead and apply our keep switch flip rule, which is keep the first one, switch to multiplication, and then flip this to 1/8. Okay, so if we go ahead and complete that process now and run through the multiplication, what should we get here?
I have 4 over 40.
4 over 40, right? Is everybody okay with 4 over 40?
No.
Would we simplify it?
Always.
1 over 10, right?
So, yeah.
Yeah, so we could simplify this because these both have a common factor of 4. So I like to write out the common factor or write the factors as a product. So we could have 4 over 4 times 10 right here at the bottom. And then the common factor of 4 will cancel out. So we should have 1/10 at the end. Right, but that's the same thing as dividing out the 4. Although notice here that if I cancel a common factor, I mentioned this last time when we were reducing fraction. When you cancel a common factor, we cancel by division. So what that means is that if we're just crossing things out willy-nilly and we're not sort of thinking about it, you might say to yourself, well, I cancel out everything on the top here, so I shouldn't put anything on the top. I should just have 10. But that's not the case. What we're really doing is saying here that we have 4 divided by 4, so we should have a 1 somewhere. So since we have 4 divided by 4 and those cancel out entirely by division, we should have this 1 here. Let's take a look at another example. Let's go with 7/2 divided by 21/3. I'm going to come up with some more problems, but you guys can go ahead and jump into these and try to solve them. Okay. And when you've completed all 3 of them, you can go ahead and use the reactions here in Zoom to throw your thumbs up so that I know that we're good. Awesome. And make sure that when you do the keep switch flip and you switch to the world of multiplication, that you, whatever the result of that multiplication is, that you fully simplify those fractions. Also, if you get stuck or have any questions, feel free to just unmute yourself and ask. Looks like we got a few people finishing up. Okay. In the interest of time, I'm going to jump in here and let's see, for those of you who have finished the first one, what should I get here? What is the answer that we should get?
7/8.
7/8. Let's see. Keep the 7/2, switch to multiplication, go to 3/21. And then in my head, I'm going to cancel this out, call that a 1, call this a 3. And I should get 3/6 for that first one. But then the 3's cancel out.
And then can we simplify that to 1/2?
Half. Yeah. Anybody have any questions about the first one?
I
done
have a
it.
question.
You may have done it a different way, and that's fine. Let's see.
Yes.
Your question.
Yeah, so whenever we get to the point where we so how you got 3/21, if that could be, we don't have to simplify that fraction.
Oh yeah, you could
leave it?
simplify that right off the bat if you wanted to. You could have called it 1/7.
Oh, okay. Oh, okay, yeah, that's what I did wrong. Okay,
Yeah.
I see. Okay,
Yeah, I mean,
thanks.
you with multiplication and division, or once you get to the multiplication step, you can reduce at any point. And sometimes reducing those fractions at the very beginning makes it a lot simpler. But if this is complicated and crazy to you, just multiply them out and then save the reducing part until the very end. You should get to the same place. And if you're not, then you just need to practice to figure out where the errors are coming up. Let's just run through these next couple. If we do the keep, switch, flip process here, we're going to keep 3/10. We're going to switch to multiplication, do 5/1. And then in my head, I'm going to simplify because I see that the 5 and the 10 will divide out. So what you might do is call this 3 times 5 on top, break this 10 into 2 times 5 times 1, and then we can cancel out the 5s. So what I should get is 3/2 for that second division problem. Okay. And then for the last one, I sort of chose these numbers not at random, right? Because I wanted to be able to simplify some stuff, or I wanted you guys to get practice simplifying stuff. So I'm going to write this as 21/8. That's going to be the same times, we're going to flip this to 4/7. And in my head, I would simplify this and call this 3 and 1, simplify this and call this 2 and 1. And so I should get 3/2 for this one as well. Okay. Now I have been known to make mistakes. If you got something different and you think that I have made a mistake, then you can send me a message later, but we're all out of time for today. So what we've covered is basic arithmetic with fractions. Gave you some simple rules for how to find common denominators. You need to be able to do that for adding and subtracting fractions. For multiplying and dividing, we're just worried about multiplication really because we're going to multiply straight across. And then for division, we learned keep, switch, flip. It takes us back to the world of multiplication. But for regardless of whatever operation we're doing with these fractions, always make sure that you take the result and fully simplify it, cancel out common factors. So now you should be ready to attack fractions 1 homework. And I'm going to open up another fractions homework. So there are 2 homeworks for fractions that will be due on Sunday. So you should get in there and practice as soon as possible so that you can come tomorrow with questions. And we can maybe take a look at some example problems out of the homework at the beginning of class. But since I'm out of time, thank you for being here. I will see you guys tomorrow, same time, same place. And if you have any other questions, well, if you don't have any questions, you're free to go. If you do, you're more than welcome to stay behind and chat, but I'll see you guys tomorrow.
Hey, Professor.